I want you to start off by imagining something with me.
Okay, I'm ready.
So imagine you are an engineer
Mm,
and you're tasked with designing this massive industrial factory.
right. Sounds like a standard Tuesday for some of our listeners,
Yeah,
honestly.
exactly. But your primary engineering challenge here isn't, optimizing the production line or like maximizing the throughput of the product. Your primary challenge is the constant, unyielding containment of an invisible, heavy, highly flammable fog.
Oh, wow. That paints a picture.
Right. And this fog is just everywhere. It wants to pool at your feet. It flows down drains like water.
Yeah, it's basically hunting for low ground.
Exactly. It's looking for basements, trenches, low-lying valleys. And if it finds like a single microscopic spark, the entire facility could be leveled in a fraction of a second.
Just instant devastation.
Yeah. And just to add, a fun layer of complexity to your design parameters,
Hmm.
the air above this invisible fog might periodically be filled with highly combustible organic dust.
It honestly sounds like an exaggerated scenario for like a fluid dynamics exam or something.
It really does. But what I'm describing is actually the baseline everyday reality at a solvent extraction plant.
Yeah, and that incredibly complex, dual threat environment is exactly why the regulatory framework we're analyzing today was even authored in the first place.
Exactly. So today, our mission is to do a complete deep dive into the 2021 edition of NFPA 36.
The standard for solvent extraction plants.
That's the one. We are looking at the literal architecture, the physical layout, and the really strict daily operational code that keeps these facilities intact.
Right, because if you're an engineer mapping out a new site or maybe a safety professional auditing an existing one,
Or just someone who's, fascinated by the hidden mathematical rules of the built environment.
absolutely, consider this your ultimate blueprint. Because we are going to look at how a facility is specifically engineered to mathematically eliminate catastrophe.
Which is such a cool way to think about it, and it's the exact right framework to use, I think.
It really is. I mean, these standards from the National Fire Protection Association, they're not just arbitrary guidelines.
Right, they aren't just bureaucratic suggestions.
No, not at all. Every single clearance distance, every ventilation requirement, every pressure calculation in NFPA 36 represents a forensic response to a past industrial failure.
A blood-written manual, basically.
Unfortunate, but true. The combination of combustible dust from, agricultural products, plus these highly volatile extraction solvents, it creates a thermodynamic environment that requires total, uncompromising operational discipline.
From both the structural design and the actual humans operating it.
Exactly.
So before an engineer can even begin to sketch a site plan, they have to intimately understand the specific physical and chemical properties of the hazard they're dealing with.
You have to know your enemy, essentially.
Right, and in solvent extraction, where they're typically taking agricultural products like soybeans or canola and extracting the vegetable oil, the primary solvent is hexane.
Yeah, hexane is the primary hazard here.
And the source material categorizes hexane as a Class IB flammable liquid. It lists a flash point of negative 26 degrees Celsius.
Which is negative 15 degrees Fahrenheit, for context.
Yeah, incredibly cold. And a boiling range starting at just 67 degrees Celsius or 153 degrees Fahrenheit.
And, those specific temperatures dictate the entire engineering approach.
How so?
Well, to understand the threat, we really have to look at what that flash point actually means in terms of vapor pressure.
Okay, unpack that for me.
So the flash point is the lowest temperature at which a liquid produces enough vapor to form an ignitable mixture in the air.
Right, reaching its lower explosive limit, or LEL.
Exactly. So at negative 26 degrees Celsius, liquid hexane is already off-gassing sufficient vapors to ignite.
Wait, really? At negative 26?
Yeah. Unless your facility is operating in the dead of an Arctic winter, your solvent is constantly in a state where it's ready to burn.
Wow. I mean, that is terrifying.
It is. And because it boils at just 67 degrees Celsius, normal industrial process heat easily transitions it entirely into a gaseous state.
Okay, but you mentioned earlier that the most critical piece of physical data provided in the annex of NFPA 36 is the vapor density.
Yes. Hexane vapors are roughly 3 times more dense than ambient air.
3 times more dense. So from a fluid dynamics perspective, this isn't like hot smoke from a fire.
Right. Smoke is buoyant, it drifts up into the atmosphere and dilutes.
But this does the exact opposite
Exactly the opposite. It does not float. It flows.
because it's so heavy.
Yeah, because of its high specific gravity relative to air, it behaves almost identically to a liquid.
I'm just picturing that heavy, rolling, dry ice fog,
Mm.
you know, like at a haunted house or a concert.
That's actually a great analogy. It will literally sheet across solid concrete surfaces. It seeks the lowest possible topological point.
So it cascades downstairs and pools around your ankles.
Exactly. And it will aggressively accumulate in pits, basements, pipe trenches, low-lying ground, anywhere it can settle.
But in this facility, it's an invisible avalanche of explosive vapor,
Yep.
not just dry ice.
Right. And it's just sitting there waiting for an ignition source.
Okay, so that brings up a chemical interaction I wanted to ask about.
Sure. What is it?
Well, the extraction process mixes this hexane with the vegetable oil to create what the text calls micella.
Ah, yes. Micella.
Right, so how does mixing a highly volatile solvent with a relatively stable heavy oil change that vapor pressure equation?
That is a critical operational variable for engineers to consider. When you create micella, you are actually altering the vapor pressure curve of the pure solvent.
Okay, so it behaves differently.
Yes. According to Raoult's law, the vapor pressure of the solvent above the mixture will be lower than the vapor pressure of the pure solvent.
Because the oil is diluting it.
Basically, yes. The oil molecules are essentially diluting the surface area where evaporation occurs.
Oh, that makes sense. So it's slightly safer.
Well, that's where you have to be careful. From a safety engineering standpoint, NFPA 36 requires you to treat micella with the exact same extreme caution as pure hexane.
Wait, even though it off-gases less?
Even though the oil suppresses the off-gassing slightly, any leak of micella will still pool on the floor.
And the hexane just evaporates out of it.
Exactly. The hexane will preferentially evaporate out of the mixture, and you will still generate that heavy, highly dense vapor cloud right at floor level.
So you can't rely on the oil to save you.
Not at all.
Man. And that heavy vapor is only 1/2 of the facility's dual threat.
Right. We haven't even talked about the dust yet.
Exactly. Because what makes solvent extraction plants so uniquely hazardous is the preparation of the agricultural materials themselves.
Yeah, before you can extract the oil using the hexane, you have to grind, flake, and condition the soybeans or sunflower seeds.
Which I imagine generates a massive volume of organic dust.
A massive volume. And we aren't talking about like nuisance dust that just makes you sneeze.
Right.
We are talking about highly combustible particulate matter.
Because when organic dust is suspended in the air at the right concentration, it has a massive surface area to mass ratio.
Exactly. And if it gets ignited, the combustion propagates from particle to particle almost instantly.
So let me get this straight. You basically have an environment where the floor and the subterranean levels are at constant risk of pooling heavy, flammable hexane vapors,
Right.
while the upper levels and adjacent preparation rooms are simultaneously generating highly combustible organic dust in the air.
That is the exact scenario.
That feels like an impossible engineering paradox. You are
No.
literally trapped between a floor that can explode and a ceiling that can explode.
It is an extreme hazard profile, no question about it. And that is exactly why the code demands a strict, non-negotiable dividing line between those two areas.
The dust-laden preparation areas and the flammable vapor-laden extraction areas.
Yes, you have to isolate them completely. Physically, structurally, and operationally.
And that isolation strategy begins at the macro level, right? Like long before the foundation is even poured.
Oh, absolutely. It begins with the sheer geography of the site.
Let's look at that geography then. Because the code mandates some severe spatial restrictions here.
Very severe.
NFPA 36 dictates that the extraction process must be sited at least 30 meters. That's 100 feet from any public way, any adjacent building, or any property line that can be built upon.
Which is a huge footprint.
It is. Furthermore, an industrial security fence must be placed at least 15 meters or 50 feet away from the extraction process.
So you are mandating a massive radius of essentially dead space.
Right. But if I'm a project engineer or a site developer, real estate is expensive. Mandating a 100-foot radial buffer of empty space in every single direction, that's a massive logistical and financial burden.
It is a massive cost, definitely.
So what is the specific physical justification for that exact distance? Like, why 100 feet?
Well, the 100-foot buffer isn't just an arbitrary real estate penalty. It is an active layer of aerodynamic defense.
Calculated based on the dispersion rate.
Exactly. Calculated based on the dispersion rate of heavy vapors.
Well-
Remember that hexane vapor is 3 times heavier than air.
Right, so it's flowing outward like water.
Yes. If you have a catastrophic rupture of a vessel, That vapor is going to rapidly flow outward from the center.
Okay.
The 100-foot clear zone provides the necessary spatial volume for ambient air currents to eventually dilute that heavy vapor cloud.
Bringing it below its lower explosive limit.
Yes, diluting it below the LEL before it can reach an uncontrolled ignition source.
Like a passing car on a public road or someone smoking on a sidewalk?
Or a boiler in a neighboring factory. Yeah. It gives the atmosphere room to neutralize the threat.
Wow. And the code also explicitly states that designers must factor in the slope of the terrain and the prevailing winds.
Which makes perfect sense when you consider the fluid nature of the vapor.
Right, because if your extraction plant is built on like a slight incline and the prevailing wind naturally blows downhill toward a neighboring property,
Then both gravity and aerodynamic drag are working together against you. They'll accelerate that heavy vapor cloud exactly where you don't want it to go.
the vapor will literally hug the terrain and flow down the incline.
Yes, and potentially pool at a neighboring site. Site engineers literally have to run topographical fluid dynamic models to prove that a potential leak will not cascade into a populated area.
I mean, that's just incredible. They have to map the literal wind and hills.
They absolutely do.
But, the code does recognize that perfect 100-foot clearances aren't always achievable.
Right, especially in existing industrial parks where space is already tight.
So if equipment absolutely must be sited closer than 100 feet, but no less than 50 feet, the code provides an engineering alternative, right?
Yes, it allows for the construction of a vapor barrier.
The standard specifies this must be a non-combustible, vapor-tight barrier at least 1.2 meters or 4 feet high.
Think of it as a physical seawall for invisible gas.
A seawall. I like that.
Since we know the vapor acts like a fluid seeking the lowest point, a 4-foot-high vapor-tight wall effectively dams the flow.
It corrals the heavy gas.
Exactly. It holds it within the restricted area and prevents it from flowing across the terrain toward external hazards.
But hold on. Creating a 4-foot vapor barrier sounds great on paper, but let's consider the operational reality of a busy industrial yard.
Okay, sure.
You have raw materials coming in, processed oil going out, maintenance crews walking around, forklifts driving everywhere.
Yeah, it's a high traffic zone.
Right. So building a literal 4-foot continuous concrete wall around your core process seems like a massive operational bottleneck. Like, how does an engineer reconcile the need for a seamless vapor-tight wall with the need for heavy machinery to actually access the equipment?
That is where the architectural ingenuity really shines. You obviously can't just have a solid 4-foot wall that forklifts have to somehow vault over.
Right, it's not a skate park.
Yeah, exactly. So engineers design physical labyrinths, or they utilize graded ramps.
Ramps, how does that work?
For instance, you might design an entrance where the roadway physically ramps up and over a 4-foot elevation change.
Yeah.
That creates a continuous topological dam, but vehicles can just drive right over it.
Oh, that's smart. The ground itself is the wall.
Exactly. Or, alternatively, you construct a staggered entry corridor.
Like a maze.
Yeah, a maze-like configuration. Because the vapor lacks the pressurized momentum to navigate sharp, staggered corners against ambient air resistance, it's effectively trapped.
Well, a forklift can just slowly navigate the turn.
Right. The barrier remains vapor-tight without requiring a literal physical gate that could accidentally be left open by a careless worker.
That is a brilliant application of passive engineering. You are shaping the terrain so the physics just do the work for you.
Passive safety is always the most reliable safety.
Absolutely. Okay, so you've sited your facility, you've modeled the wind and the topography, you've constructed your vapor seawalls. Now you have to engineer the actual extraction building itself.
The fortress.
The fortress. The code states the building must be fire-resistive or non-combustible. But the most absolute, unyielding structural rule I saw was regarding the foundation.
Oh, the basement rule.
Yeah, there can be absolutely no basements, no enclosed tunnels, no pipe trenches, and no pits below grade within 100 feet of the extraction process.
Which, based on our discussion of vapor density earlier, the mechanism behind that rule should be glaringly clear.
Right, because a basement or a pipe trench would effectively be a custom-built subterranean catchment basin for explosive gas.
Precisely. If you have a slow, microscopic leak of hexane somewhere in the facility, that heavy vapor will constantly seep downward.
And if you have a basement or a trench,
That vapor will quietly displace the air and accumulate down there over days or even weeks.
and because hexane vapor is invisible and the area is subterranean, this accumulation goes completely undetected.
Completely undetected. Until a maintenance worker goes down into that pit with a steel wrench, strikes a piece of concrete, causes a spark.
And initiates a massive explosion.
Exactly. So the code eliminates this risk by simply outlawing the geometry that allows it to happen in the first place.
You cannot build a void below grade, period.
Period.
But the standard also forces engineers to confront the limits of prevention, right?
Okay.
Even with perfect topographical planning and zero basements, you have to design for the worst-case scenario.
You have to assume containment will eventually fail.
Right. What happens when a primary containment failure occurs and the gas actually ignites inside the building?
This leads us to the 1 to 15 rule for explosion relief.
Yes. The code mandates that for every 15 cubic meters of building volume, there must be at least 1 square meter of explosion relief area.
And this brings up a really critical distinction in explosion dynamics, the difference between a deflagration and a detonation.
Let's pause and drill down into that, actually, because those terms are often used interchangeably in casual conversation or movies.
Right, people just say explosion.
But in structural engineering, they represent entirely different physical forces, don't they?
Completely different. The difference is all about the speed of the combustion wave.
Okay, explain.
In a deflagration, the flame front and the resulting pressure wave travel through the unburned gas at subsonic speeds.
So slower than the speed of sound.
Exactly. But in a detonation, the reaction is supersonic. It creates an immediate catastrophic shockwave.
Okay, so what are we dealing with in a hexane plant?
Fortunately, an unconfined or semi-confined hexane vapor cloud ignition typically results in a subsonic deflagration.
Okay, so it's a bit slower.
Relatively speaking, yes. But as the gas burns, it still expands rapidly, creating an immense buildup of pressure inside the building.
And if you build an unbreakable, heavily reinforced concrete box,
Then that subsonic pressure wave will build up against those rigid walls until the structural limits of the concrete are finally exceeded.
and when the concrete finally fails, it fails catastrophically.
Exactly. The entire structural skeleton collapses. You've essentially built a giant fragmentation grenade that will send heavy concrete shrapnel flying across your 100-foot buffer zone.
That is a terrifying image.
Yes.
So instead of trying to contain the pressure,
Explosion relief engineering intentionally builds structural weaknesses into the envelope of the building.
you literally designed it to break.
Yes. The code gives examples. Light non-combustible wall panels, roof hatches, or top-hinged windows with special explosion relief latches.
And these panels are engineered with a very specific burst pressure.
Exactly. When the subsonic pressure wave from the deflagration hits, the specialized latches on these panels yield instantly.
Because the pressure wave is subsonic, the physical panels actually have the milliseconds required to mechanically open and get out of the way, right?
That's the key. They get out of the way before the pressure exceeds the load-bearing capacity of the building's main steel skeleton.
So the building essentially opens its mouth and exhales the explosion.
Exactly. The pressure is vented harmlessly outward into that calculated 100-foot empty buffer zone, while the primary columns and beams holding the roof up remain perfectly intact.
You sacrifice the skin of the building to save its bones.
And, more importantly, you save the lives of anyone nearby.
It is a profound shift in perspective. You really aren't building a fortress to keep the energy in. You're building a highly calibrated release valve.
That's a perfect way to summarize it.
So if the superstructure is designed to handle the airborne threat of a pressure wave, how do engineers manage the liquid threat?
Ah, the liquid threat.
Yeah, say a massive transfer pipe shears off, and suddenly you have hundreds of gallons of highly flammable liquid hexane violently pouring onto the floor.
Well, this transitions us from structural architectural defense to mechanical fluid management. A massive liquid spill is a worst-case scenario because of the sheer volume of volatile fuel involved. If that liquid hexane is allowed to flow indiscriminately, it will quickly exceed the evaporative capacity of your ventilation systems.
And even worse, if that liquid solvent finds its way into the municipal sewer system,
Oh, that's a nightmare. It will flow underground beneath the city, off-gassing its heavy vapors directly into the sewer mains.
you will have effectively turned the subterranean infrastructure of the surrounding town into a bomb.
Yes, which is unacceptable. So to mathematically eliminate that possibility, the code dictates the creation of a specialized fluid management network.
Right. The standard requires that all solid upper floors of the extraction process and the main concrete pads underneath the process equipment must be physically curbed.
There has to be a raised concrete lip around the entire perimeter.
Furthermore, the floor itself cannot be perfectly flat, right? It must be specifically sloped.
Sloped to drain directly away from the center, feeding into an external separation sump.
Let's focus deeply on the mechanics of that separation sump, because reading about it, it is a masterpiece of passive safety engineering.
It really is. It requires no electronics, no sensors, and no moving parts.
Nothing that can break during a power outage.
Exactly. A separation sump leverages fundamental chemical properties, specifically immiscibility and specific gravity, to automatically triage a disaster.
Okay, walk me through the precise fluid dynamics of this sump.
Sure.
If I have a catastrophic pipe rupture and a chaotic mixture of liquid hexane, micella, and maybe fire suppression water is rushing down the sloped floors and pouring into this concrete basin, how does a static concrete box separate the bomb from the water supply?
We have to look at the specific gravity of the liquids involved.
Okay.
Water has a specific gravity of 1.0. Hexane is significantly lighter, with a specific gravity of roughly 0.66.
Okay, so it's lighter.
Furthermore, hexane and water are immiscible. They chemically refuse to mix with each other.
Right.
So when that chaotic slurry of water and solvent hits the primary retention section of the sump, gravity immediately begins to sort it out.
The heavier water sinks to the bottom.
Exactly. While the lighter, highly volatile solvent floats entirely on the surface.
Just like oil and vinegar separating in a jar.
Yes, but on a massive, highly dangerous industrial scale.
Okay, so they separate. Then what?
Well, the genius of the sump design lies in the underflow weir, or water seal wall.
What does that look like?
Inside the basin, there is a concrete baffle or wall that extends deep down into the water layer, but it stops just short of the very bottom.
Leaving a gap at the floor of the sump.
Right, so the heavier water at the bottom flows easily underneath this wall and out toward the municipal sewer, or the safe wastewater treatment area.
But the highly flammable hexane, which is floating on top of the water layer, sits well above the bottom opening of that wall.
Yes, it is physically trapped by the concrete barrier. It cannot dive down to flow underneath it.
Because it's too light.
Exactly. The hazardous solvent is perfectly contained in the retention section, riding on top of the water, while the safe water continues to flow out underneath it.
The bomb is separated from the public infrastructure purely by gravity and geometry.
It's elegant, isn't it?
It's amazing.
Yeah.
But, calculating the size of this retention basin must be a massive engineering headache.
Oh, sizing it's a whole other challenge.
Because you have to anticipate exactly how much liquid could possibly spill in a disaster. How does the code mandate the volumetric capacity of this sump?
The math here is very unforgiving. NFPA 36 states the sump must be sized to hold the entire design solvent spill volume from the largest single vessel or isolated pipe network in the facility.
Okay, the largest single vessel.
Plus an additional 50% of that maximum volume.
Wait, 50% more. So if an engineer calculates that the largest extractor tank holds, say, 10,000 gallons of salt,
the retention section of the sump must be built to hold 15,000 gallons of pure solvent.
that's a massive margin of error. Why mandate such a huge excess capacity?
Because a massive solvent spill rarely happens in a vacuum. It is usually accompanied by a fire.
Oh, right.
If a vessel ruptures and ignites, your automated fire suppression deluge systems are going to activate immediately.
And they dump a lot of water.
Those systems might be dumping thousands of gallons of water per minute into the facility, and all of that water is mixing with the spilled solvent and rushing straight into the sump.
I see. So while the water will eventually flow under the weir, the initial massive influx could raise the total liquid level in the basin dynamically.
Exactly. You need that 50% volumetric buffer to ensure the floating layer of hexane does not simply rise up and overflow the exterior walls of the sump before the water can drain away.
Because if the sump overflows, the solvent escapes the containment zone entirely.
And the entire passive defense system fails.
It's all about accommodating the worst-case surge dynamics.
You have to plan for the worst possible minute of the worst possible day.
Okay, so we've mapped out the macro-level defenses. We have the 100-foot dispersion buffer, the topographical vapor walls, the subterranean bands, the deflagration blowout panels, and the gravity-fed separation sumps.
That's a solid fortress.
It is. So let's move inward and examine the specific mechanical safeguards on the processing equipment itself.
Let's do it.
Earlier, we established that the facility must strictly isolate the dusty agricultural preparation area from the volatile vapor extraction area.
Yes, complete isolation.
But you still have to actually move the crushed seeds from the prep room into the extraction room, right? Like physically transport them.
You do.
So if you run a conveyor belt through a hole in the wall, haven't you just breached your own fortress?
You absolutely have. A standard conveyor chute going through a firewall provides a direct, unhindered tunnel for heavy hexane vapors to flow backwards,
Right out of the extraction area and directly into the dust-laden preparation room.
which completely violates the primary isolation directive we talked about.
Yeah.
So how does the code address this? I mean, you can't exactly put a solid steel door over a conveyor belt that is actively moving tons of soybeans.
No, you can't. So NFPA 36 requires the implementation of vapor seals on all conveyors entering or leaving the extraction process.
What does a vapor seal look like on a moving conveyor?
Well, the most elegant way this is achieved is by utilizing the agricultural product itself as the sealing mechanism.
Wait, using the soybeans?
Yes. Engineers design specific conveyor configurations, often utilizing inclined augers or rotary airlock valves.
Okay.
These are designed to ensure that a dense, highly compacted, continuous plug of the crushed seed or meal is constantly blocking the cross-section of the chute.
So because the auger is always packed tight with the physical soybeans,
Yes.
there's just no open airspace for the vapor to travel through.
Exactly. The product you're processing becomes the physical cork in the bottle.
That is so clever. The solid mass of the agricultural material provides enough physical resistance to stop the low-pressure solvent vapors from migrating backward.
It seals the breach dynamically while still allowing thousands of pounds of material throughput.
Okay, so that handles mechanical connection points. But what about the primary atmospheric venting?
Venting is critical.
The code dictates that the extraction process must be a closed system, and it must be vented to the outside atmosphere.
Right.
But crucially, these vent discharge pipes must terminate at least 6 meters or 20 feet above the ground.
And that 20-foot elevation rule ties directly back to our earlier discussion on vapor density.
Because it's heavy.
Yes. During normal operations, the system will naturally breathe and off-gas small amounts of hexane.
And if you vented that gas at ground level,
The heavy vapor would immediately pool right around the base of the equipment, creating an invisible puddle of fuel.
but by pushing the discharge point 20 feet into the air,
You are forcing the vapor into higher velocity atmospheric wind currents. This drastically increases its dispersion and dilution rate before gravity can pull it back down to a potential ignition source at ground level.
that makes total sense. But running a 20-foot pipe connected directly to a tank full of boiling hexane seems like you've just built a giant fuse.
A giant fuse. Yeah, I could see why you'd say that.
I mean, if a lightning strike or an external fire ignites the vapor cloud venting out of the top of that pipe, won't the flame front just follow the fuel source straight down the pipe and into the main extraction vessel?
That is the exact hazard scenario the code anticipates, which is why it mandates that all vent lines must be equipped with approved flame arresters.
Okay, I'm looking at the concept of a flame arrestor. And my initial instinct is to picture like a one-way mechanical check valve or something.
Like a flapper that closes.
Yeah, but gas has to be able to flow out constantly.
Yeah.
So how does a stationary piece of hardware inside an open pipe actually stop a flame front from traveling backward? Is it choking off the oxygen?
It actually doesn't rely on choking the oxygen, and it has absolutely zero mechanical moving parts.
So how does it work?
It relies entirely on rapid thermodynamics. A flame arrestor is essentially a tightly wound matrix of corrugated metal ribbon or a really dense metal grid inserted inside the pipe.
Okay.
It contains hundreds of tiny parallel channels. Gas can easily flow through these small channels without restriction.
But fire can't.
To understand how it stops a fire, we have to look at a concept called the minimum experimental safe gap, or MESG, and the quenching distance of the specific gas.
Okay, break that down for me. How does the metal matrix interact with the actual fire?
When the external vapor ignites at the top of the pipe, a flame front begins accelerating down the pipe toward the tank.
Right.
But for a flame to even exist, it requires a continuous generation of heat. When the flame front hits the metal matrix of the flame arrestor, it is physically forced to divide into those hundreds of tiny channels.
Okay, it gets chopped up.
Exactly. And the massive surface area of the cold metal surrounding those tiny channels rapidly absorbs the thermal energy from the flame.
Like sucks the heat out.
It absorbs the heat so incredibly fast that the temperature of the reacting gas drops below its auto-ignition temperature.
Wow.
The flame is literally chilled to death in a matter of milliseconds. The flame front is extinguished, and the fire physically cannot pass through the matrix to the other side.
That is incredible. It is just a thermal heat sink designed to murder a flame front.
That's exactly what it is.
But what happens during the periods when the plant isn't running in a steady, closed state?
Ah, transitional states.
Right. When you are shutting the plant down for maintenance or starting it up from cold, the code notes that the internal atmosphere of the equipment actually passes through the flammable range.
And this is without a doubt one of the most perilous phases of operation.
Why is that?
Because during normal, steady-state extraction, the inside of a sealed vessel might actually be too rich to burn.
Too rich.
Yeah, the atmosphere inside is so heavily saturated with hexane vapor well above the upper explosive limit, or UEL, that there simply isn't enough oxygen present to support combustion.
Oh, it's like a flooded car engine.
Yeah.
There's just too much fuel and not enough air to spark.
Exactly. But when you shut the plant down and begin to introduce ambient air, or when you are starting up a dry plant and slowly introducing the solvent,
The ratio changes.
the ratio of solvent vapor to oxygen shifts drastically. The atmosphere must inevitably cross through the danger zone, the space between the lower explosive limit and the upper explosive limit.
This is the flammable range, where the stoichiometry is perfectly balanced for a catastrophic explosion if a static spark occurs.
Yes. And to safely bridge this transitional danger zone, the code mandates a procedure known as inerting.
Inerting. Okay, so the strategy here is not just hoping you avoid a spark. It is a mathematical elimination of the combustion equation.
Precisely.
To have a fire, you need a specific atmospheric composition. We know we have the fuel, the hexane, but instead of just trying to manage the fuel, inerting attacks the oxidizer.
We focus on a metric called the limiting oxygen concentration, or LOC. Hexane requires a specific minimum percentage of atmospheric oxygen to ignite, regardless of how much fuel is present in the tank.
Okay.
To prevent ignition during startup or shutdown, operators inject an inert, non-reactive gas, usually nitrogen or carbon dioxide, directly into the vessels.
Pushing out the regular air.
The inert gas violently displaces the ambient air, pushing the oxygen concentration deep below the LOC threshold.
Meaning, if the oxygen concentration is below the LOC, an explosion is mathematically and chemically impossible, even if you literally struck a match inside the tank.
Exactly. You hold the equipment in this chemically inert, oxygen-starved state. Once you verify via instrumentation that the oxygen levels are safe, you can then safely introduce the liquid hexane during startup,
Or safely purge the remaining vapors during shutdown.
without ever crossing through an ignitable atmospheric mixture.
So through rigorous physics and chemistry, the engineers have designed a seemingly perfect structural and mechanical fortress.
It's as perfect as engineering allows.
You have the topographical barriers, the deflagration relief systems, the immiscible fluid sumps, the thermal flame arresters, and the chemical inerting protocols.
It's a lot of layers.
It is. But this brings us to the ultimate point of failure in any engineered system:
Human beings.
human beings. None of the automated physics matter if the people operating the plant bypass them.
Human behavior and operational complacency are always the most unpredictable variables in safety engineering.
Because the most sophisticated PLC interlock system can be defeated by a maintenance worker taking a shortcut.
It happens all the time. Therefore, Chapter 4 of NFPA 36 shifts entirely from mechanical engineering to strict, uncompromising behavioral codes within the restricted area.
And the rules within this zone are absolute. No smoking, obviously. No matches or lighters can even be carried past the perimeter fence.
Standard protocol.
Powered vehicles like forklifts are strictly prohibited unless they are highly specialized approved units.
Right.
But the detail that really highlights the extreme nature of this environment is the rule regarding hand tools.
No.
You can't even use a standard flashlight.
No, you absolutely cannot.
The code states that any flashlight must be specifically approved for Class I Group D locations.
And to understand why a simple flashlight is heavily regulated, we must discuss intrinsic safety and minimum ignition energy, or MIE.
Okay, MIE.
Every flammable gas has an MIE. That is the absolute minimum amount of thermal or electrical energy, measured in millijoules, required to ignite it.
Okay.
When you slide the plastic switch on a standard hardware store flashlight, two metal contacts touch, creating a microscopic, practically invisible electrical arc inside the casing.
And in my kitchen, that microarc means absolutely nothing.
Nothing at all. But in a restricted area where hexane vapors might have pooled around your ankles,
Oh, wow.
that invisible microarc contains more than enough millijoules of energy to exceed the MIE of hexane. The flashlight literally becomes the detonator.
That is terrifying.
So, equipment approved for Class I, Group D locations is intrinsically safe. This means the internal electrical circuitry is specifically engineered to aggressively limit the voltage and current available.
So even if it breaks.
Even in the event of a dead short circuit, or if the bulb shatters completely, The device physically cannot release enough joules of thermal or electrical energy to reach the ignition threshold of the specific vapor.
It is an incredible level of microscopic detail.
It has to be.
And the human element also extends to basic housekeeping. We discussed the combustible organic dust from the soybeans earlier.
Right, the dust overhead.
The code mandates the daily removal of all waste and oily rags. But there is a very specific prohibition regarding how you clean that dust.
Very specific.
You are strictly forbidden from using compressed air blowdowns to clean machinery unless the entire extraction process is completely shut down and locked out.
Right.
Why is blowing dust off a motor so dangerous? Mechanics do it all the time.
It comes back to the fundamental mechanics of a dust explosion. A thick layer of combustible dust sitting statically on a beam or a motor casing is certainly a fire hazard,
Sure.
but it is not an immediate explosion hazard because it lacks suspension and surface area exposure to oxygen.
Oh, I see where this is going.
When a worker takes a high-pressure air wand and blasts that dust off the motor, they are violently suspending millions of microscopic organic particles into the air.
Perfectly mixing them with ambient oxygen.
They are artificially engineering an optimal, highly explosive dust cloud right in front of themselves.
Wow.
And if that air wand also happens to agitate a failing bearing in the motor that sparks, that worker has just initiated a primary dust deflagration.
So what's the alternative? How do you clean it?
The code mandates vacuuming. You must use specialized, intrinsically safe vacuum systems to suck the dust away, removing the fuel load without ever allowing it to become suspended in the atmosphere.
Which sounds like an agonizingly slow, deliberate way to work.
It is much slower than an air wand, but it won't kill you.
Fair point. But let's look at a scenario where significant work actually needs to be done. Industrial machinery breaks, pipes rust, flanges leak.
Constantly.
If a maintenance engineer needs to cut out a section of rusted pipe, and they need to use an angle grinder or an arc welder, they are deliberately introducing a massive source of thermal energy and sparks right into the fortress.
Yes.
How does the code reconcile the necessity of maintenance with the absolute prohibition of sparks?
They reconcile it through extreme operational friction. Taking a grinder to a pipe in a solvent extraction plant is a nightmare scenario.
I can imagine.
To do it legally under NFPA 36, a facility must execute a rigorous safety work permit system. It's universally known in the industry as hot work.
I reviewed the sample permit in Annex C of the code, and honestly, it is exhausting just to read.
It's meant to be.
It is not just a supervisor's signature. Let's walk through the grueling reality of what it actually takes for a maintenance worker to just cut a piece of pipe.
Okay. Before a single tool is even powered on, the specific section of pipe must be completely emptied of all product.
Naturally.
Then it must be physically isolated. This means executing a strict lockout to or a low-tow procedure.
Okay, turning off the valves.
And often installing physical metal blanks, solid metal plates between the pipe flanges to guarantee that no upstream valves can accidentally leak hexane vapor back into the work area.
But even an isolated, completely empty pipe is dangerous, right? Because the internal walls of the steel are still coated in residual solvent, off-gassing vapor.
Exactly. Which leads to the purging phase.
Purging.
Maintenance crews will pipe high-pressure steam directly into the isolated vessel or pipe. The immense thermal energy of the steam boils off the residual liquid solvent.
And the steam pressure physically forces the explosive gas out through external vents.
They will boil the inside of the equipment for hours to ensure every single molecule of solvent is expelled.
So they've isolated the pipe, they've boiled the pipe with steam for hours, but the permit still isn't approved.
No. Absolutely not. Once the steaming is complete, a specialized technician must utilize a calibrated combustible gas indicator, often a photoionization detector, or PID,
To sniff the air.
to sniff the internal atmosphere of the pipe. They have to scientifically prove, with documented numbers, that the atmosphere is completely free of volatile organic compounds.
And then they can cut.
Only after the gas tests come back completely clean, and only after continuous ventilation is established in the surrounding area, is the permit actually signed.
And the friction doesn't stop once the work starts either.
Nope.
The permit requires continuous atmospheric monitoring while the grinding or welding is actually occurring. A dedicated fire watch stands by with an extinguisher.
And if the gas monitor detects even a fraction of a % of the lower explosive limit, all tools are killed instantly, Work stops.
I just marvel at the operational discipline required here. It is the absolute antithesis of the move fast and break things tech culture.
Oh, completely. In this environment, it is move agonizingly slow,
Yeah.
verify the physics 3 times, and absolutely do not break the containment.
And that operational friction must cost the facility massive amounts of money in lost production time.
It does, but the code enforces it because the alternative is an immediate loss of the entire facility and all the lives within it.
It's a sobering reality. However, despite all the structural fortresses, the fluid dynamic sumps and the grueling hot work permits, we have to acknowledge reality.
Things still go wrong.
Mechanical systems fatigue. Human beings err. Things go critically wrong. A pump seal blows out or a bearing seizes and ignites.
It happens.
Which brings us to our final segment, emergency stoppage and fire protection. What happens when the alarms actually sound?
Well, a properly engineered NFPA 36 facility does not rely solely on human intervention during a crisis.
Good. Humans panic.
Right. It protects itself automatically through a highly integrated system of programmable logic controllers, or PLCs, and mechanical interlocks.
So the system monitors its own vital signs.
Yes. The code dictates centrally located alarms that trigger instantly upon the loss of steam pressure, the loss of cooling water flow, or a primary pump failure.
But the facility doesn't just sound a siren and wait for a human to diagnose the issue, does it?
No, it initiates a calculated physical response.
The code details a specific interlock stoppage cascade for the mechanical equipment moving the solid soybeans. Let's look at that.
Sure.
Say an extraction auger jams up and seizes. The code states that the equipment feeding that jammed auger must automatically shut down, but the equipment taking material away from it must keep running.
If you think about the mechanical torque involved, this is a brilliant piece of cascade logic.
Why is that?
If an auger seizes and the conveyor belt feeding it continues to dump tons of crushed seeds into the chute, you will instantly create a massive, compacted mechanical bottleneck.
A huge jam.
And the friction from the slipping belts and straining motors trying to push against that immovable jam will generate immense heat.
Rapidly exceeding ignition temperatures.
Exactly. But by utilizing PLC logic gates, the system recognizes the fault. It automatically starves the jam by instantly killing the upstream feed,
But it deliberately commands the downstream equipment to keep running.
effectively pulling material away and emptying the line behind the jam. It clears the bottleneck dynamically without any human intervention.
That is just algorithmic logic applied to massive rotating steel.
It's very cool.
But let's escalate the scenario to a full-scale plant emergency. A major fire breaks out. The plant manager hits the massive emergency stop button, intending to kill the entire extraction process.
Okay, the big red button.
The code dictates what I'm calling the golden rule of shutdown.
Yes, this is crucial.
It explicitly states that during an emergency shutdown, smothering steam, cooling water flowing to the condensers, and the primary exhaust fans must absolutely not be shut down.
This represents one of the most critical thermodynamic requirements in the entire standard.
Because human instinct says otherwise.
Right. When an untrained person panics during a fire, their instinct is to kill the main breaker, to shut off all power, close all valves, stop everything.
But if you kill the main power to an extraction plant,
You will likely cause a secondary explosion far worse than the initial fire.
walk me through the physics of that cascading failure. Why is killing the power so dangerous?
First, consider the exhaust fans. If you kill the power to the ventilation system, those heavy hexane vapors are no longer being actively pulled out of the extraction building and pushed 20 feet into the air.
Right, the 20-foot vents we talked about.
They just stop.
Yes.
So the vapors will immediately begin to sink, pool on the floor, and spread rapidly toward the existing fire. You are basically allowing the fuel to freely seek the ignition source.
Okay, that's bad. What's the second reason?
Second, and much more critically, consider the cooling water. Your massive solvent storage tanks and condensers are completely full of volatile liquid.
Okay.
If a fire is raging nearby, the ambient temperature in the room is skyrocketing. If you shut off the coolant water flowing over those condensers, the liquid inside those sealed tanks will begin to boil violently from the ambient heat.
The heat transfers right through the steel, boils the liquid, and because the tank is sealed tight.
The internal pressure begins to climb exponentially.
And eventually, the pressure exceeds the structural yield strength of the steel vessel.
Yes. The tank violently ruptures, instantly depressurizing the superheated liquid solvent. The liquid flashes into a massive vapor cloud in milliseconds and immediately ignites.
Which is known as a BOV, Right.
Yes, a boiling liquid expanding vapor explosion. A BOV will instantly level the building and produce a thermal shockwave that can easily destroy neighboring facilities.
It is entirely counterintuitive until you understand the thermodynamics. In a catastrophic emergency, you must kill the material feed, you must stop the solvent transfer pumps, but you must intentionally keep the cooling water and the ventilation fans running on emergency backup power.
You have to actively bleed off the internal heat and bleed off the atmospheric pressure, or your fortress literally turns into a supersonic bomb.
You are maintaining the critical life support systems of the pressure vessels even as you abandon the production line.
Exactly. And while those cooling systems fight to prevent a BLEV, the active fire extinguishing systems deploy.
The code mandates that the massive internal extractors must be protected by internal extinguishing systems utilizing inert gas, steam, or both, flooded directly into the machines from a remote location.
Pushing the atmosphere back below that limiting oxygen concentration we discussed earlier.
And for the structural envelope of the building itself, the code mandates heavy water spray or deluge systems.
And returning to our BLEV discussion, those deluge systems are not just there to extinguish the flames on the floor.
They aren't.
No, they are specifically engineered to provide exact densities of water flow over the structural steel columns and the exterior shells of the storage tanks.
To keep them cool.
Yes, the immense volume of water acts as a thermal shield, continuously cooling the metal to prevent structural fatigue and to keep the internal solvent temperatures stable while the fire is actually fought.
Wow. It is truly an engineered symphony.
It really is.
Designing a compliant, safe solvent extraction plant is a symphony of spatial topography, fluid dynamics, organic chemistry, thermodynamics, and unrelenting operational discipline.
All working together.
We began this deep dive discussing an invisible, heavy, highly flammable fog and a suffocating cloud of combustible dust.
The dual threat.
And we have methodically seen how every single dimension dictated by this code is a specific mathematical answer to a deadly physics problem.
And that is the ultimate realization for any engineer, designer, or safety professional engaging with this standard. NFPA 36 is not a checklist of bureaucratic suggestions.
Not at all.
A 4-foot topographical vapor dam, a 20-foot atmospheric vent pipe, an immiscible separation sump size with a 150% margin of error, and an intrinsically safe flashlight. These are not random requirements.
They're calculated.
They are the rigorous mathematical translation of chemical properties into physical safety architecture. When you execute this code, you are not merely achieving compliance, you are literally engineering the possibility of disaster out of existence.
I think that is the perfect, definitive place to conclude our deep dive into this standard today.
It's been a fascinating topic.
It really has. But I want to leave you, our listener, with a final thought to mull over as you go about your week.
What's that?
The next time you are driving down a long stretch of highway, or maybe taking a commuter train past a sprawling industrial park, and you see a massive, quiet industrial facility sitting seemingly isolated in the exact center of a huge, empty, fenced-off field. Consider what we've discussed today.
It's not just an empty field.
Exactly. That empty space isn't just an unmaintained lawn. It isn't just surplus real estate waiting for a future warehouse.
It's a tool.
It is a carefully calculated, heavily regulated aerodynamic safety buffer. It is an active architectural defense mechanism designed to dilute the invisible forces of nature.
It really makes you see the built world differently.
It does. It makes you wonder, as we navigate our heavily built world, what other invisible architectural barriers, what other unseen mathematical moats do we casually walk past every single day without ever realizing they are actively keeping us alive?